Hello students, your physics teacher Hassan Darwish with you. In this video, I am going to explain the mechanical oscillation of a simple pendulum. This is part of chapter 4, Mechanical Oscillations. But what is a simple pendulum? In reality, a simple pendulum is an idealized model consisting of a point mass suspended by a massless inextensible string. Here it is. We have a massless string or rod to this free end suspended at point O, and to this free end we attach a particle, a small marble. Now this is the equilibrium position as I explained at the beginning of the chapter. Now if you displace this pendulum slightly from the equilibrium and then release it, then it will oscillate around or vibrate around the equilibrium position. So this system is called simple pendulum. Now we want to find or to determine the proper period of this simple pendulum. But in reality, it is a limiting case or a special case of a compound pendulum. Now, since the simple pendulum is a special case of a compound pendulum or idealized case, we can deduce its proper period or natural period of oscillation from that of the compound pendulum. How? Let's do it. Now, the natural period of the compound pendulum for compound pendulum the period, you know, it is T0 equal to pi radical I, which is the moment of inertia of the pendulum, over m, which is the total mass of the pendulum, g, gravity of the planet, and a, where a represents the position of the center of mass relative to the axis of oscillation. Here the axis of oscillation delta is where? At point O, point of suspension. Now we have a particle A only. So I of the particle is, you know, mr squared equal ml squared. Here is a particle and here is delta, and this is the length of the string. M is the mass of the particle, and A, which is equal in reality OG. So we have only one particle here, where G is here. So this is equal to L, because we have only one particle. Replace everything here, we get what? We get, in this case, the period of the simple pendulum, 2 pi radical L over G. Okay, this is in reality the proper period or the natural period of a simple pendulum. But let's do the calculation from the beginning. Means let's obtain the second order differential equation and the nature of motion, as we did for each pendulum, compound and torsion, and elastic also. Okay, at any time we always apply the principle of conservation of mechanical energy. At any time the mechanical energy is kinetic energy and potential energy. Here gravitational potential energy. Now for a particle, half mv squared, right? Also you can say, some students say, because we have circular motion, I can say half I theta prime squared. This is true. But if you replace I and theta prime, you get half mv squared. I verified this before. Plus mgh. Okay? So let's replace. Half m. V is r theta prime. Here r radius of the circle is L. Theta prime squared. Plus mg. Now we need h. Let's go back to the figure to find h. This is the reference potential. Choose it here in the equilibrium position. Sorry. Reference level for the potential. And this is h. Let's make projection on this level to benefit from theta and the length of the string. So call this h. Now what is h? H is hc. Okay? So here, let me do it here. H is equal to hc. And this is equal hc, this part, small part, is OC minus OH. Okay? OC minus OH. But OC is the length of the string, L. And OH, if you apply cosine theta in the right angle triangle, you get L cosine theta. So H becomes L into 1 minus cosine theta, right? Okay, let's replace it here. We get half m L squared theta prime squared plus mg L into 1 minus cosine theta. This is the expression of the mechanical energy of the simple pendulum at any instant, any time. If we want to obtain the differential equation, we have to make derivative for this equation. Since there are no dissipative forces, we can say mechanical energy is conserved. Okay? This means mechanical energy equal constant. Okay, good. So what's the derivative of a constant? Me prime equal derivative. I emphasize here on the derivative with respect to time. d over dt equal to 0. So let's make derivative of our expression. Half m L squared constant, but multiplicative constant. Derivative of theta prime squared is like the derivative of u squared in mathematics. It is 2 theta prime theta double prime. And derivative of cosine theta in mathematics like the derivative of cosine u, which is minus sine u times u prime. Okay? Do this here. We get m L squared theta prime theta double prime plus mgl into derivative of minus cosine. Cosine is sine theta times theta prime, and all of this equal to 0. Now we have here ml, okay, and here we have ml, and this is theta prime, theta prime. So you know that ml theta prime different from 0, and divide by L, we get this differential equation. Theta double prime plus G over L sine theta equal to 0. This is the second order differential equation, and as I explained in the previous videos, we call it second order because this is the second derivative. Okay? The function, don't forget, the function is theta. This is the function which varies with time. And this is the derivative of the second derivative of the function. Now the question is that, the important question, is the motion of this pendulum simple harmonic motion? Of course no, not simple harmonic motion. Why is this? Since the differential equation, as I did with compound pendulum, differential equation not of the form y double prime plus omega 0 squared y equal to 0. Okay? Here there is theta double prime, but here there is sine theta. But we always choose or take the case of small amplitude oscillations. What do you mean by small amplitude oscillations? The angle must be smaller than 10 degrees. We choose theta always smaller than or equal 10 degrees. In this case, I can make the approximation. Sine theta approximately equal to theta in radian. You can make sure of this from your calculator. Okay? So replace it now in the differential equation. We get theta double prime plus G over L, theta equal to 0. So this is the second order differential equation, which is of this form. Okay? Of the form y double prime plus omega 0 squared y equal to 0. Hence, simple harmonic motion. Why is this? Since the solution is of the form is theta equal theta m, as I did in the first video. Okay? Theta m, cosine or sine doesn't matter, omega 0 b plus phi. So notice here the angle theta is a complicated function. You see, it's a sinusoidal function. You know, omega 0, which is the angular frequency, equal what? G over L, right? If you make the comparison, omega 0 squared is G over L, right? Implies omega 0 is a radical G over L, and consequently the proper period, which is 2 pi over omega 0, becomes 2 pi radical L over G. Okay? The same as obtained from the compound pendulum. And you know that theta m represents the amplitude, which is a constant obtained from the initial conditions, and phi the initial phase. Okay, this is the study of the simple pendulum. See you in the next video. Bye bye.